So the first part of this talks about writing style and usage. You can read through that. The second part of this talks about the report, the paper. This is the standard format. Standard format is going to have a title, byline, abstract, introduction, experimental results, discussion. This is pretty much the standard format. Sometimes they call the sections by different names. And so let's start our paper here. So I started this morning. So the first section that we need is the title. So let's read this. The best time to determine the title is after you've written the text, because the title should reflect the paper's content and emphasis accurately and clearly. If a medium iron alloy is better than a magnetic alloy. The title must be brief and grammatically correct, but accurate and complete enough to stand alone. A 2 or 3 word title may be too vague, but a 14 or 15 word title is probably unnecessarily long. Avoid phrases like on the, a study of, research on, report on, regarding, and use of. In most cases, omit the, rapid, and you. In books, but not in journals, you cannot come up with a title that is short enough. Consider breaking it into title and subtitle. Okay. The title should attract the potential audience and aid retrieval and indexing services, so it is important to include several key words. Series titles are of little value. Spell out and define each new term and avoid jargon, symbols, formulas, and abbreviations. Whenever possible, use words rather than formulas and abbreviations. Whenever possible, use words rather than expressions containing superscripts, subscripts, or other special notations. Do not cite company names or specific trademarks or instruments or materials in titles. And so we can come up with a simple title for our paper. Our paper was a synthesis. You can resize my window if you want to have a window of your own as well. But what did we make? What was that stuff called that we had made? So, for example, you can have my paper on half the monitor and yours on the other half. So you can resize it.
Was our product potassium oxalated chloride? Trioxalated chloride.
Potassium trioxalate. I guess we don't really need parentheses there. But maybe we'll put it in there. Trioxalato chromate.
Correct.
Roman numeral Is it resizing? Let me do this. I'm going to just make it this size, normal size. Why don't you resize my window and then you can open up the Word file for yourself. We'll put the formula in here as well. The search. So it's K3CROX3. Then I'm going to insert a dot here. Let's see. By going to symbol, more symbols, and then looking for a dot. Which looks like this one here. 3H2O, and then I'll write salt. I'm going to center this here. We could have more details in there or just leave it. We'll just leave it. Because the abstract will give us more information. So. The next section is the byline and affiliation. Include in the byline all of those and only those who have made substantial contributions to the work, even if the paper has actually been written by only one person. Use first names, initials, and surnames. Well, it depends on the journal. Some journals want you to spell out your first name, others want you to use an initial, so you have to look at the journal. But whatever journal it is, follow their rules and make sure all the names are consistent with one another. Do not include professional or official titles or academic degrees. The first author and the last author are generally considered the senior authors, unless there's only one author. Indicate the author to whom correspondence should be addressed with an asterisk or superscript. The affiliation should be the institution where the work was conducted. If the present address of an author differs from that at which the work was done, give the current address in the footnote. All right, so I would write out my first name, let's say middle initial, and then last name. And then I'll give an affiliation where the work was done. The next section is the abstract. The abstract is a one-paragraph summary of the entire paper. It's like the Cliff Notes version of your paper. A lot of people don't have time to read the whole paper. So all they want to do is read a little summary which tells them what the key findings were in the paper. So let's say you don't have enough time to watch the movie. You have your friend tell you what happened. You know, they want to know everything that happened. And so it's the same thing here. You're going to condense everything that happened in this paper into one paragraph. That way, everybody knows the ending, and the ending is what your key finding or conclusion was. So let's see what they say here. Many publications require that an informative abstract accompany every paper. For a research paper, the abstract should summarize the principal findings. For a review paper, the abstract should describe the topic, the scope, the sources reviewed, and the conclusions. You should write the abstract last to be sure that it reflects accurately the content of the paper. So there are different kinds of paper. There's a research paper which we're writing based on our laboratory work. And there's a review paper. A review paper is, let's say you wanted to know the state of the art of a particular field. Let's say you know nothing about it and you're trying to learn about this field. Then the best thing to do is read all the review papers on that particular field, because what the review papers do is they give a review of everything that's happened in the field since the beginning all the way to the current state of the art. And so it describes who all the key scientists, researchers who are working in the field and what their contribution to that particular field was or is. So a review paper is very useful if you're trying to learn a new subject. But we're not writing a review paper. It also says to write the abstract last. That's normally what's done. You know, you'll write the paper and then you'll write a one paragraph summary or synopsis of the whole entire paper. It has to stand alone, this abstract. As often as published separately. In fact, you can get books of abstracts and just read the abstracts, and if you find something that's interesting, then you get the entire paper. Online, you can find abstracts. So here, published in the Royal Society of Chemistry is an abstract. Actually, this looks to be the whole paper. But when we do a search, let's do... I'm going to do a Google Scholar search. And I'm going to look up some synthesis papers. So if I go to this one, synthesis of piperidines, click on this. This is a review paper. This is talking about the synthesis of piperidines from the beginning here, and it talks about, you know, the key contributions of this from various groups. However, if I look at this one, synthesis of oxytocin, actually this is the full paper here as well. This is interesting. Oh no, this is just the abstract. So we have the abstract here. It's a one paragraph. If you want to read the whole paper, then typically you have to pay for it, which is odd. So let's take a look. Okay, this one, oh, this is very interesting. They're giving us the whole first page. But normally, if you want more than the abstract, and this is all they give you is the abstract here, then you have to pay for it. So if I wanted the complete paper, I'd have to get rights and content. And then I'd have to purchase it, basically. But at least we can read the abstract. So instead of writing the abstract last, we're going to write the abstract first. Normally, the abstract is formatted a little differently than the paper itself. So if we go back to looking at some of these other papers here, the PDF version, let me get the PDF. You see the abstract here is formatted a little differently than the rest. The rest of the paper has columns here. The abstract is formatted across the entire page. And so we normally format the abstract a little differently. And so I'm going to do the same thing here. What I'm going to do is I'm going to indent the margins, let's say. So you can show the ruler or view the ruler, and then I'm going to indent the margins like, let's say, a ½ inch here. And the reason I'm going to write the abstract first is to give us an outline of what the paper is going to be. Normally we do it again in the opposite direction, but in this case I want an outline of what I'm going to talk about. And so what I'm going to say is I'm just going to copy this. Potassium trioxalate 3 trihydrate, K3CrOX3.3H2O, solid, was, now we're describing what we did. So it was synthesized. Well, this is pretty much saying what we said on the title. So we need a little bit more detail here. And so it was synthesized from what? What were our starting materials for this synthesis?
Potassium dichromate?
Yes, was synthesized from potassium dichromate. What else? Oxalic acid. The oxalic acid was a monohydrate, so I'll write in monohydrate. Anything else?
Potassium oxalate.
Potassium oxalate. Was that it? Ethanol. But the ethanol is kind of used in a funny way.
The potassium oxalate was
The potassium oxalate was the hydrate?
Yes.
All right. Potassium oxalate monohydrate. How about the Oxalic acid. Was that anhydrous or monohydrate as well?
Anhydrous.
Anhydrous. Okay, let's get rid of that. Thanks. And potassium oxalate monohydrate. Ethanol was used to do what? Ethanol was used for solvent exchange precipitation by metathesis of the product. Say something like that. So let's see what they say about the abstract here. The purposes of the abstract are to allow the reader to determine the nature and scope of the information given in the paper. So most readers only read the abstract. Like 99% of the people who read your paper will stop after they finish the abstract. A small percentage will go on and read the entire paper, and those are the people who are more directly related to the field. The other purpose of the paper is for keyword searches. And so there's certain keywords that should go in there for indexing and eventual retrieval via database searches. The abstract must contain sufficient information to allow a reader to decide whether to read the whole paper, which like 99% choose not to usually. But there are certain papers that are really relevant to your field of study that are must-reads, and so you'll have to get those. At our library, we don't subscribe to very many journals. So if you go to like UCLA or Cal State, they have a subscription where you can get the papers. You don't have to pay. But if you were to pay for the papers, they're like $25, $35 per paper. There are sites where they try to publish papers without the fee, but not all papers are on that particular site. The abstract should provide adequate data for generating index entries for database searches, although an abstract should not be a substitute for the article itself. Yeah, the abstract can't contain all the information, all the details. It must be complete enough to appear separately in abstract publications. Often authors' abstracts are used directly in chemical abstracts. Chemical abstracts is the abstract database for the American Chemical Society. In the abstract, you should briefly state the problem or the purpose of the research. For us, the purpose of the research was to synthesize that compound. When that information is not adequately contained in the title, so we didn't really, I guess we did synthesis, so it's kind of the same thing here. But we're going to add a few more details than the title. Indicate the theoretical or experimental plan used. So ours was the experimental plan, which is the synthesis. Accurately summarize the principal findings and point out major conclusions. Include chemical safety information when applicable. Do not add to, evaluate, or comment on conclusions in the text. So the abstract and the main text, they need to stand alone, and you shouldn't find extra information in the abstract that you don't find in the regular paper. The abstract should be concise and self-contained. The optimum length could be 2 sentences. It could be many more, depending on the subject matter and the length of the paper. Use meaningful nomenclature, that is. Use standard systematic nomenclature where specificity and complexity require, or use trivial nomenclature that will be adequately and ambiguously defined, for a well-established compound. Do not cite references, tables, figures, or sections of the paper. You may refer to equations or structures presented in the body of the paper if they are on a single line and can readily be incorporated when the abstract is used in the secondary literature. Do not include equations and structures that take up more than one line. Use abbreviations and acronyms sparingly and only when necessary to prevent awkward construction or needless repetition. Define abbreviations at first use in the abstract and again at first use in the text. So this might be too much because we're repeating what we had in the title here. But then, since this stands alone, we'll just leave it. And so this compound was synthesized from potassium dichromate, oxalic acid, and potassium oxalate monohydrate. Ethanol was used for solvent exchange precipitation by metathesis for the product. We'll clean this up later. And so our purpose is just to get a rough draft today. We could add more details, so this would be like a 2-sentence abstract. If we wanted to provide more detail, we could say stuff like dichromate. Dichromate ion was reduced. Actually, maybe change that. Dichromate has chromium 6, so maybe we'll just say chromium 6 was reduced to chromium 3. Chromium 6 was reduced to chromium 3 using oxalic acid, which was oxidized to CO2, carbon dioxide, in a vigorous reaction. Vigorous reactions part safety because a vigorous reaction can soon turn into an out of control reaction. Oxalate, a bidentate chelating agent, oxalate, a bidentate chelating agent. We can say there are different words we can use for this. This is going to be a Lewis acid-base reaction. And so oxalate, a bidentate chelating agent, the Lewis base, reacted with chromium 3 ions, the Lewis acid. Ethanol was used for solvent exchange precipitation by metathesis of the product. The product was isolated and washed with ethanol. We haven't quite finished this, so there's going to be more to this abstract. But we just want to get a start on the abstract now. Typically, we format the abstract a little differently. So what I'm going to do is I might change this to block here. I might indent this a little bit more. And then I might change the font size, go a little bit smaller and bold. Or actually, I'll keep it 11 point. So now our abstract's getting a little bit longer. We'll rewrite it with time, but for now, let's go on to the next section. The next section is the introduction section. A good introduction is a clear statement of the problem or project and why you are studying it. So a clear statement of the project for us is we're synthesizing this compound. But why are we studying it? Why you're studying it is because you're kind of forced to synthesize it for Chem 1B. But normally, that's not what we'd write. Normally, what you do is you read the review. And as you read the review of a particular system, like, for example, this, the trisoxalato chromate 3 complex, then maybe questions come up, like certain questions about its structure or properties. Or maybe there's holes when you look at a full review of the field of trisoxalato chromate 3 complexes. And maybe this fills the hole or answers some questions. Since we know nothing about the field, and since maybe there's a review article. If there's a review article online, then that's probably the best place to start to learn a little something about the field. What we're going to do for the introduction is we're just going to try to do some research to understand what's been done in this, or why study this, why make it, what's it used for. And so we'll want to find, maybe it occurs naturally. Does it occur in nature, or was this made in a laboratory? We'd like to know. Well, anyway, this information should be contained in the first few sentences. On the basis of your answer to the question of what the readers already know, give a concise background of the problem and the significant scope and limits of your work. So we want to show how our work fits in to the field of this. Outline what has been done before by citing truly pertinent literature, but do not include a general survey of semi-relevant literature. So we want you to cite the most important, the most significant work, but not give a full review. Otherwise, you're writing a review paper, not a research paper. State how your work differs from work previously published, or state how it is related. Demonstrate the continuity from the previous work to yours. Your introduction should be at least 1 or 2 paragraphs long. Ordinarily, the heading introduction is not used because it is superfluous. Opening paragraphs are usually introductory in nature. So normally it's not used, but in some papers it is used. Like here, it's not used. If we look at this, here we have the abstract synthesis of oxytocin. This is published by the Journal of American Chemical Society. The abstracts are free, but the full paper costs money. And so here we have the title. This one has a footnote, though. Footnote 1. A preliminary report of this work appeared, so in the different in this journal here. This is the byline. Normally we don't say by Vincent too. They just write the names out. This is older, 1954, so they have it. Usually you have a date here as well. And then the abstract. They talk about it, the synthesis. And then here they give a little review of it. You know, oxytocin, the principle, etc., etc. So then you can read about it. And then you'll read about how this fits into that whole scheme of things. So we're going to go ahead and use the heading introduction here. And what we'll want to do is we want to give some kind of either some kind of mention about the history of this compound, you know, potassium trioxide and chromate 3, or trioxide and chromate 3, or potassium trioxide and chromate 3 trihydrate. Like the significance, why bother making this stuff? And maybe something about the synthetic method that we're using, etc. So the introduction, you'll have to do some research to figure out. And as far as research goes, you could take a look at what's been done. And to take a look at what's been done, we could take a look at search engines like Google Scholar. And see what we can find. So here we can find crystal structure and electron paramagnetic resonance studies, etc. So you'll take a look and see there's some stuff of interest there. All right, after the introduction comes the experimental details or theoretical basis. This goes by other names, like the experimental section or materials and methods. We're just going to call it the experimental section. In the experimental section, what we want to do is we just want to describe the procedure that we use to make this stuff. For experimental work, give enough detail about your materials and methods so that other experienced workers could repeat your work and obtain comparable results. So normally we tell them how much and of what, and how they were mixed or manipulated so that somebody else could follow along the experimental section and get the exact same results. Identify the materials you used and give information on the degree and criteria for purity, but do not reference standard laboratory reagents like solvents and HCl and that kind of stuff. Give the chemical names of all compounds and the chemical formulas of compounds that are new or uncommon. So the names and formulas, if it's new and uncommon, or just the name. Describe your apparatus only if it is not standard and not commercially available. So one apparatus that we used was vacuum filtration. The vacuum filtration, that's kind of standard in a way. In another way, this is non-standard because this is not made by company. This is just like a homemade vacuum filtration apparatus, i.e. the tubing, everything, was commercially made, but assembling all the parts together was homemade. So we could include a figure for that in our paper. Here. If we bought an apparatus that was complete, then we would just give the company name and model number in parentheses as adequate and non-distracting for that apparatus. Avoid using trademarks and brand names of equipment and reagents. Use generic names. Include the trademark in parentheses after the generic name only if the product you used is somehow different from others. Furthermore, trade names often are recognized and available as such only in the country of origin. So some products have some kind of trade names like all the different names that you can have for hydrochloric acid or muriatic acid, pool acid, etc., etc. Describe the procedures you used unless they are established in standard. An established and standard procedure is like going to the balance and weighing a solid. You don't have to describe that. You just say what the mass of the solid is. And so people don't want to read that you walked over to the balance and then you weighed your sample, walked back to your lab station. Those are just standard. But people will want to know, how you mix the chemicals. Note and emphasize any hazards such as explosive tendencies and toxicity in a separate paragraph introduced by the word caution. Include precautionary handling procedures and any other safety considerations. Some ACS journals and books will also indicate the hazard as a footnote on their contents pages. In theoretical reports, okay, this is not a theoretical report. Theoretical report would just do a lot of math. And so let's go back to this. So what we do is we describe exactly what we did, in enough detail that somebody could repeat it. And so one of the things they might want to repeat is trying to get the exact same amount. And so it said to get 3.6 grams. Let's say I got 3.68 grams. So write that. That's slightly off. 3.6 grams of potassium dichromate was slowly added to beaker. We don't necessarily have to write in there because you could use other glassware in addition to beakers. And so in this case, what we'll say is was slowly added to 10. Let's say I weighed out 10.33 grams of oxalic acid. Suspension. In how much water? 20 milliliters of water. Mm-hmm. We use DI water, so I'm just going to write DI water. DI stands for deionized, not distilled, and so we can spell it out also. But there are common abbreviations. Deionized. Yeah, we could write in about 20 milliliters. That's fine. We can say caution, because there's a safety concern here. Caution. This vigorous reaction generated heat and gas, carbon dioxide gas. Then what happened? Let's say after the reaction subsided, let's say I got 4.22 grams. You use your amounts. 4.22 grams of potassium oxalate monohydrate. Was added to the black product suspension and heated for 10 minutes. We can say approximately 10 minutes also, if you want. Okay, then what did we do? The reaction mixture was cooled. Did you add the ethanol in the ice bath, or did you add it after cooling to room temperature? After cooling in the ice bath? Okay. The reaction mixture was cooled in an ice water bath. And how many milliliters of ethanol did you add? Oh, okay, and 10 milliliters of 95% ethanol. Was mixed with stirring. Did you stir it? Yeah, then you could add that in there. What color were the crystals? Blue-green crystals, the product. Do you know about how big they were? Pretty small, like half a millimeter. Okay, blue-green, say, comma, 0.5 millimeter. Well, we didn't really measure it, did we? The crystals were isolated by vacuum filtration and washed with 3 10 milliliter Well, I have a word here, aliquots. It would be like portions. 3 10 milliliter aliquots of 95% ethanol. Followed by 1 25 milliliter. Was it?
It was 50 the first three.
The first 3 were 50. Okay. And the last 25 was 95. The let's say the approximately 3 millimeter crystals. What would you guess?
Probably half to one.
Hmm?
Half a millimeter to 1 meter.
Half to 1 millimeter. Okay. Those are estimated to be 0.5 to 1 millimeter in dimension. The crystals were then dissolved in a minimum of water. How much water was used? Well, it was dissolved in, let's say mine took 5 milliliters of water. In order to recrystallize. All right, we're still working on the procedure. But one of the things we can do is we can talk about the purity and the manufacture of the potassium dichromate. So when you buy potassium dichromate, there are a number of manufacturers you can purchase it from. So for example, Sigma Aldrich. Did anybody write down the information on the bottle? Does anybody know who the manufacturer of that was? And what grade it was? We buy the cheap stuff. The cheap stuff is called technical grade. You can buy the expensive stuff as well. So for example, this is high grade. This is NIST traceable product 1.02. And this is $110 for 80 grams. It's kind of expensive. We like technical grade. And so this is a potassium dichromate, fine granules, technical grade from Fisher Chemical. Here we can buy 500 grams for $282. Or 3 kilograms, 3,000 grams, for $684. So this is way cheaper, but it's a much lower grade. Technical grade is considered a good quality chemical grade for educational purposes and has a purity around 85 to 90%, but it is not pure enough for food and drug applications. Our technical grade's probably better than this. Our technical grade's probably in the 90% range. What are the grades of chemicals? Let's take a look. There are more than just technical. ACS grade is the highest grade. ACS grade, this grade is acceptable for food, drug, or medicinal use and can be used for ACS applications or for general procedures that require stringent specifications. And so ACS and reagent grade are high. Actually, there's one more grade that's not on here. It's called analytical grade. Analytical grade is even higher. Surprisingly, food grade is down low. Food grade chemicals are I think around technical grade. Then we have reagent grade. Reagent grade is typically what I used a lot of. Reagent grade and ACS grade are about the same, but they're cheaper than analytical grade. Analytical grade are for quantitative analysis. USP grade for medicinal use. This is pharmaceutical grade. NF grade, laboratory grade, purified grade, technical grade. Technical grade is not pure enough for food, drug, or medicinal use of any kind. And so when you buy a bottle of this stuff, we know what the purity is, and so here we can include it in here. So we can say what the purity is, because when you buy a bottle of this stuff, they give you the spec, the analytical specs. That is, they tell us what the purity is and what the common contaminants or impurities in there. So from the spec sheet, we can see how much lead is in there, what percentage, etc. Okay, the oxalic acid, I don't remember, but we'll take a look at these. So these will be corrected later, but I'm sure it's technical grade because we can't afford much more than that. The ethanol, that's a common reagent. And so nobody buys high purity ethanol, really. Not unless you're doing a synthesis with it specifically. And so that's a common lab chemical. We don't have to write that out for common lab chemicals. All right, so we're going to continue with the experimental section as we complete the lab. After the experimental section comes the results. The results are often combined with the discussion section. And they're a little bit different. The results are just the facts of the experiment, So, for example, one of the facts of the experiment is you got these crystals. But is it a fact that those crystals are 100% pure potassium trioxalato chromate 3? What do you think? Probably not, because what somebody is going to want to see is they're going to want to see proof. Did you make 100% pure or 99.9% pure? What is the purity of that? And therefore, in a typical synthesis paper, let me plug that into Google Scholar here. When we do a synthesis paper, take a look. I'm going to write in synthesis here. And one of the things that pops up or populates the search is synthesis and characterization. This is very common. Take a look at these papers, synthesis and characterization, etc. Synthesis and characterization go hand in hand. Because you might make this stuff, but how are you going to prove this stuff is good? Well, how you prove this stuff is good is by characterizing it. And so characterization is you figure out, is the stuff you're telling me that you made is actually the stuff you made? How can you prove it? In other words, how can you prove those little black, blue, green crystals are actually trioxalato chromate 3? Is there a way you can prove it to me? No. And next is, how can you prove what the purity is? And so this is typically what's done in characterization. In characterization, you're confirming that what you think you made is actually what you made. And this is important because, in our paper, we're saying that we're using potassium dichromate from Sigma Aldrich, technical grade. That's fine if it's a brand new bottle. If it's a brand new bottle, you crack it open, you know what the purity of that is. But let's say it's an old bottle that's been used by hundreds and hundreds of students. Do you think they might have contaminated it? Yeah, contamination could be a big issue there. Or even if you buy a bottle, like there's a very famous story at MIT, Lincoln Lab, and I think they pulled a bottle off the shelf. And this bottle had been sitting there. And it turned out they did like a couple of years worth of research, assuming that the bottle label described the bottle contents. It turned out the contents of the bottle was different than the label. They didn't know that. And so they had to fix all their papers. It turned out it wasn't a complete disaster because once they figured out what was in the bottle, then they could adjust all their data appropriately. But even with brand new stuff like this, the potassium dichromate, we characterize that before we use it, because if you're going to invest a lot of time and money into making something, then you want to make sure the starting material is what they say it is. And so we do some quick tests of the starting material to make sure it's the stuff that it's the right stuff and it's of sufficient purity. And so that's all part of the characterization process there. Now, when it comes to results, we are not going to speculate anything. The results are just going to be what we made. Okay, and so in our results, we say how many grams. I don't know how many grams we're going to end up with, but I think the theoretical yield was around 10 grams or something. So we'll just say X, once we dry it, X, hopefully we get double-digit grams. So X.XX grams. Now, I'd like to say it was pure, 100% pure potassium trioxalato, but I can't. And so what I'm going to say is I'm just going to say something that I can say is we did get 100% pure black, blue, green crystals. So X.XX grams of blue, I don't know if we should maybe black, blue, green crystals obtained. Okay, that's it for results. That's what we can say factually, and that's what results should prove, because somebody else might say, hey, I don't believe those black, blue, green crystals are what you say they are. I disagree. And so they can take your results and come up with a completely different interpretation of the results. So in the discussion section, what we need to do here is we need to prove that what we made is what we think we made. In other words, we're going to discuss why we think what we have, why we think these black, blue, green crystals are indeed potassium trioxalato chromate 3 trihydrate. And so how are you going to do that? How are you going to prove it? Well, normally we can prove it quite quickly by using very expensive laboratory equipment that can analyze, solids and whatnot quite quickly. So, for example, if we know what the crystal structure of this is, then I can do something called a powder X-ray diffraction. XRD, it's called powder X-ray diffraction. And basically, from that, we get a fingerprint, and that fingerprint we can compare with the fingerprint of pure potassium trioxalato chromate 3. And if they match, if the two fingerprints match, then that's pretty good proof right there. But we don't have a powder X-ray diffraction available to us. And so we have to use other means. What are some other means that people use to characterize? Some other means that, like water. How would you characterize if your water were pure? Boiling point. Well, ours is a solid, so the boiling point is going to be quite high. So instead of using the boiling point, we could try using the melting point. So what temperature does potassium trioxylatochromate 3 melt at? And so we'll have to find out. We'll have to search the literature to find out what the melting point is. And then we'd have to measure our melting point. And if the two melting points agree, that's good. But if they're off, then that's very concerning. But if we don't measure the melting point, is there some other way we can do it? Did you get the melting point?
Yeah,
There is no melting point?
not applicable.
All right, then I guess we don't have it. Because usually if there's no melting point, that means you start heating it and then it decomposes. You know, rather than melt, it'll catch on fire or do something else like that. So if you tried to melt wood, have you ever tried to melt wood? It's not going to melt, it's going to decompose. So anyway, so we don't have melting, so you know how we're going to do it? We're going to try to convince the reader that we have the chemistry down. That is, you know, based on the synthetic procedure that we use, the method that we used, we can convince them that what we have is what we think we have, you know, based on the chemistry.
So right here it says that it has a boiling point up to 65 Celsius.
Oh, then
so
we could try to,
we would try to
yeah,
boil
we
it
could,
in,
yeah.
thermometer and prove.
Right. Then we can
Okay.
try to prove it that way.
Okay.
Right, exactly. That's good. Anyway, in the discussion, we're going to try to do this without characterization. Our paper is just synthesis. There's no characterization. If we had synthesis and characterization, then we're fully characterizing this. But since this is just synthesis, that's all we got. And so what we're going to do is, before we get into the discussion, we're going to do some maybe some background research for the introduction, and then you should start thinking, you know, about the synthetic methodology. And based on this synthetic methodology, we go through it step by step, explaining to the reader each step of the synthesis we're doing, and then seeing, does that make sense, you know, these reactions.
So that would include like talking about the reduction and oxidation properties and everything.
Right, exactly. And so, and then I'll write the rough draft with you guys here, and then you can just clean it up. So this first paper we'll do together like this. We're going to do 2 of these, and the next paper you'll try to do it on your own. So this first one, and on Wednesday we're coming back in here. So on Wednesday we'll finish up the rough draft, do the discussion. Okay. And so why don't you do some research for the introduction in the last 15 minutes class here.